what their power is, you need to know their limits. Right? If you know there are limits, well, that means there's a limit to their power. Right? So you learn something about the extent of their power. You know, what class of languages can they accept, recognize? Right? Now, what this session's about is it's going to prove that there are languages that cannot be recognized by any finite automaton. Right? You know, hence non-regular languages. There are some languages, they just have no finite automaton that recognizes them. Okay? Hence you label them non-regular. You know, non-regular in the sense of like normal, conventional, average. Okay? Oh, the expression, he's a regular guy, that just means, he's a normal guy, he's not crazy, he's just sort of an average person. Right? So a regular language, so a non-regular language. Well, let's do an example. Just throw out a simple example for you. We've been using the capital letter A for languages. To make a contrast of a non-regular language, use a different letter, call it B. Okay, so B is a language, and it's a set of strings. That's what a language is. Right? And the string take the following form: 0 to the n, 1 to the n. And what that means? Remember what that means? That you just have a concatenation of n zeros, just n of them, n zeros in a row, okay? In a substring, followed by n ones, like a substring of ones of length n. So your string now is n zeros followed by n ones. That's it. But your n is any non-negative integer. Okay? It can be 0 or more. Okay? Non-negative integer. Now, if it's 0, this would just be the empty string times the empty string, which is just the empty string. So it'd just be epsilon. Right? You just have epsilon here. Okay. Now, why is that language non-regular? So why does this language not have a finite automaton that recognizes it? Well, the clue is the word finite in your finite automaton. Okay? What does that? I mean, refresher. What is a finite automaton? Well, it's an automaton with a finite number of states. Now, is that all? Is that all it is? Is that sufficient definition? Well, anyway, it's all we need for this purpose. Okay? Because if you're going to accept a given string, you need to count how many zeros there were. You need to know that, okay, so that you can count the number of ones that follow. Okay, common sense, makes sense. But n is anything. N is any positive, well, non-negative integer. Okay, good. It can be huge. There's no limit, and that means the amount of memory that you need to be able to count the number of zeros, that will be some function of n. Well, n could be effectively infinite, right? Therefore, the amount of resources, the amount of memory that you need in that finite automaton, in fact, is not finite, becomes infinite, right? Therefore, there is no finite automaton that can recognize this language, because this language demands infinite memory, right, to be able to count the number of zeros, because n can go to infinity. Okay, does that sound plausible? Right? So we have done our first example of a language that is non-regular, right? There is no finite automaton that can recognize it. All right. That's what I'm saying. The number of zeros is not limited. Okay? So your finite, well, deterministic finite automaton would need to have infinite resources, infinite amount of memory to be able to count the number of zeros. Alright, now this is a bit of a lead-in now to the next couple of sessions. There's an important proof. I'll give you its name, jumping ahead a little. It's called the pumping, like to pump, like pumping air into a tyre, a bicycle tyre, car tyre, pump. So it's called the pumping lemma, and it's called a lemma, but it's effectively a theorem. And this theorem is used to help prove that a particular language is regular. Right? So just think of, you don't know what it is yet. Just think of this so-called pumping lemma, which is a theorem. You can use it to prove whether a language is regular or not. Okay? That's what we're heading towards. Okay, so we're going to show a method that proves that a language is not regular. So you can use that pumping lemma to disprove that something is regular. You can use either way. Right. Now, but this creates a bit of a puzzle because why do you need this sort of proof? Why do you need this pumping lemma? Isn't it sort of obvious that the fact that the number of zeros is unlimited and therefore that language has to be non-regular? Doesn't that seem obvious? Why do you need this proof? Well, because things get a bit complicated. Your intuition might, common sense in a sense. You look at a particular language and you say, oh, well, that's obviously non-regular because it, by appearance, looking at it, it looks as though it needs infinite memory, infinite resources, and therefore no finite automaton could possibly recognize it. And that's what you're being warned against, because appearances can be deceptive, right? You can be fooled. So there are languages that look as though they cannot. They look as though they're non-regular. In other words, these languages look as though there's no finite automaton that could recognize them, but in fact they are. Those languages are regular, that there is some finite automaton that can recognize it. So you need something more rigorous, and so you'll use this pumping theorem. That provides the rigor, the proof whether a language is regular or non-regular. Okay. All right. So now to give you a taste of. Give you two languages. Now both of them give the appearance, when you look at them superficially, that both of them would be non-regular languages. Both of them look as though they need like infinite memory to be able to recognize them as to recognize them. Okay. Now it turns out that one of them is non-regular, and the other one is surprisingly regular, despite the appearance that it's not. The appearance is that it has that it needs infinite memory, but in fact, turns out that it can be recognized by a finite automaton that needs only a finite number of states, finite amount of memory to recognize the language. Okay, so. Is it getting a little dark? Maybe I really should get this whole process going earlier in the day. I'll switch on the light. I don't want it telling me not enough light. But now that I have paper over it, I'm curious to see how yesterday's filming will come out with YouTube after the YouTube's correction. It says, not enough light, would you like us to fix it? And I say yes. I'm curious to see how it came out with now the paper over the lampshades. The cylindrical, transparent glass lampshades with the bulb inside. Alright, so two languages. Language C and language D. Now, the alphabet is just the binary alphabet, 0 and 1, and C is the language of strings, W, and W has an equal number of zeros and ones. Each string has an equal number of zeros and ones in it. Okay, now before I ask you which is which one do you think is the non-regular and which one is the regular? Yeah, there's one of each. Okay, D, the other language, D, it's a set of strings, W, and W has an equal number of occurrences, the number of times it happens, of 0, 1 and 1, 0 as substrings. Okay? So you scan along your W, and each time you see a 0, 1 consecutive, neighbouring 0, 1, you increment the count of the number of 0, 1s. And each time you see a 1, 0 consecutive, 1, and its right-hand neighbour is 0. Each time you see that, you increment its count. Okay, the W belongs to this language if the final count you get of 0, 1 is equal to the number count you get of 1, 0. Okay. Now, intuitively, you're going to need infinite sources to count the number of zeros, and infinite resources to count the number of ones to be able to compare them to see if they're equal, right? So it looks as though C requires infinite memory and therefore cannot be detected by a finite automaton, right? So C looks as though it's non-regular language. What about D? Well, similar story, right? You think this string could be of any length at all. It's not restricted, so there's no limit on the number of appearances of 0, 1. And similar comment for the number of appearances of 1, 0. So it looks as though to be able to compare the count of this and the count of that, to be able to compare them, see if they're equal. So it looks as though D also is a non-regular language, that it requires infinite memory. Now, it turns out, at first glance, the machine, you need infinite memory for both. Now, it works out, C, let me just check, C is the one that is non-regular, okay? And D is actually regular, because there are tricks you can do that allow you to count this and this, but with finite resources, with finite memory. In fact, you might try to do that. Try that as. In fact, I think it's one of the exercises at the end of the chapter to actually do that. To actually create, design a DFA, I think, that recognises language D. Right?